Okay, so I'm coming down to day 5, to data cleaning. And first, we're just gonna summarize some of the things that we've talked about. So remember, yesterday we talked about summarization, and we learned that when we use the summary function, we get quantile information about data. But if we use the summarize function, that helps us to get specific information based on functions like mean or sum that we can do for particular variables. If we use the across function, which is a little bit tricky and advanced, we can select multiple columns and summarize multiple columns simultaneously. So if this is difficult for you, don't worry, because you can always just do the same steps multiple times on each column. And then we had our count function, which is super helpful for looking at the unique number of values and how many counts there are for each of those, which is a great thing to keep in mind and continue to use to check your data. We have the group by function, which helps us to change all subsequent functions. So if we wanted to look at how our data is summarized for a specific group, we can use group by first. And then we used plot and his to make pretty cool, quick plots just to get a quick view of our data. But we'll talk later about fancier visualizations. Okay, and this is not as long ago as it would have been because we did some of this just now, but as a recap on our classes, our tibbles show our classes. So when we use glimpse or we just type the tibble name, we can see what the classes are for the variables, and that's really useful. So you can make sure that your date data is actually a date. Remember that the logic class, you have to use true or false without quotes. And if you want to coerce anything to a particular class, you could do as character, as numeric, etc. We used rep, seek, and sample to create vectors. This one repeats, this one makes a sequence, this one makes a random sample. And then we talked about matrices and lists and the looper date package. Okay, so now onto data cleaning, and I basically have time to just say why data cleaning matters. And so this is one of the most important steps of a data analysis, actually, and it takes a lot of time typically. I know in my work, this is usually the longest process, is getting my data ready. So it's, checking your data for inaccuracies or missing data, recoding it in a way that makes it just work much more easily for you. So this could be renaming your variables, which you've already done some on, but it could also be looking at the actual values and changing those values. So that's what we'll be looking at today. But most importantly, first most important rule, just take a look at your data. Use all those functions that we've told you about, like glimpse and skim from the skimmer package, but also just view or scrolling through your data. Take a look, see if there's anything strange. Okay, so we're going to talk for quite a bit about missing data because this is a really important topic. So there's actually a variety of missing data that you can have. You can have just general missing data, which we've already covered a little bit, which would be NA or not available. And then there's also occasionally what you'll find is NaN, which stands for not a number. And that happens when you do, for example, 0 divided by 0. And then occasionally you might run into infinity or negative infinity, which happens when you divide either a positive number or a negative number by 0, respectively. And so it's important to find this data because before you start using big summary functions or start plotting it, you might, or doing analyses, you might end up with results that you don't expect because, as we talked about yesterday, if you have NA values, sometimes your functions won't work, or we'll see in a bit that you might get results that you don't necessarily expect or intend. So how do you check for these? So there's functions that are pretty simple for each of these. Is NA, is NaN, and is infinite, that looks for each of them. The only kind of tricky part here is that is NA looks for both NaN and NA, not just NA, whereas the other two are specifically for that type of data. So as an example here, I've made some test data that has all of these different forms. So I have a 0, an NA value, and a -1, and I've divided it all by a 0, which gives me a NaN, an NA, and a negative infinity. And so if I do is NA on this, I get true, true, because these are conditional functions that just assess if a value is NA or not. So here we're looking, is this NA, and NaN, like I said, will be counted by NA as NA, as is the NA value. And then of course our NaN comes up only for the NaN, and our infinite comes up for the infinite. There's also a really helpful function called any, which is asking to get across the entire vector in this case, are there any values that is NA? So do we have any values that have NAs? So for example, here we have 1 value in A and 0 values in B that are NA. So if we do any is NA on A, we just get the output of one single true or false, and the answer is true. There's 1 NA, and for B it is false. Okay, so we talked about the count function yesterday to summarize our data, and it's super helpful for looking for NA values because other summary functions don't necessarily do this, but like in base R, the count is great because it actually includes them. And so here we can see with our bike data that we used yesterday, when we count the subtype variable, we see that there are 4 observations that are NA. So that's a really great way to check your data. It's a little bit easier when we're actually using data frames to use something like count as opposed to the is NA or any is NA. But occasionally you might need it for a vector or if you're doing something detailed. But there's also a really great package called Nanyar, which was named apparently after Narnia a bit. Anyway, there's a whole story about why it's got this name and information about it at this link. And it's a great option for visualizing and finding information about missing data. Importantly, it doesn't look for infinite values because those are considered a value. It's just not an NA. So, you know, keep that in mind if you're doing anything where you might actually have an infinite value. But so for example, here, we would need to install packages Nanyar if you were using it for the first time and load it with library. And there's all kinds of great functions. One that we're going to talk about is %complete. So PCT stands for percent, which shows the percentage that's complete for the entire data frame. So it gives you a nice summary of how much data might be missing. So here we can see on this X vector that 85% is complete. So the rest of it is incomplete. Here, looking at our test data where we had NaN, NA, and inf, you can see that it may not work as you expect because the infinite value is counted as complete. So this also works on data frames. So we're gonna just pull up a data frame here using the air quality data. So if you type in !air quality, you'll find out information about this. And we can make a tibble out of it using the tibble function. And when we look inside, we see something like this, where we have ozone, which has an Na value or 2. Solar.R has some Na values. And wind, temp, month, day, at least for the part that we can see, look complete. So we can use our nannyr %complete function on this data frame, and we can see that 95% of it is complete. And that's helpful to know that we have 5% that's missing. But even more helpful is this function called ggmiss variable, so ggmissvar. So we're looking for, GG typically stands for grammar of graphics. They're looking at images or plots, so that's why this is called that, and it's looking for missing variables. And this creates a really nice plot that shows the number of missing values for each variable. So we can see that for the ozone variable, we have greater than 30 missing values. And we also have some for the solar data, but the rest of the data is indeed complete. So that kind of matches with, oops, what we were seeing here, where we saw the Na values for these two. But now we know that it's mostly ozone that's missing. All right, so we talked yesterday about how when we use the summarize function, sometimes when we use mathematical notation, we also did this on basic R day, that if we have Na values, this will result in an Na unless we put the Na.remove equals true argument. Which would look like this. So just wanted to point out, this is also true for logical data. So remember, we just learned yesterday that logical data is true or false without any quotations around it. If we have an Na value for that type of data, again, we'll get an Na as a result. So recall that true is evaluated as 1 and false is evaluated as 0. So here, if we were to sum this up, ideally we would get 4 because there's 4 trues, because it would be 4 plus 0. But because of the Na value, we get an Na. If we do the Na.remove equals true, we get a sum of 4. All right, so an important note about the filter function. When you use filter, it will automatically remove missing values because R can't determine if they meet the condition that you're filtering by, because those Na values could be anything. So if we're filtering for greater than 2 for a particular value, that Na could be 1,000, it could be 0. There's no way of knowing. So those values get filtered out. If you want to keep your Na values, you can add a compound conditional with the or to show that you want it is Na data. So we'll show that in just a second. So here I have a data frame that has a dog and cat variable, and I have some Na values here. And if I filter for less than 3 for the dog variable, I'll see that both the 3 data and the Na row got removed. But if I add the or argument and then is Na here for the dog variable, then I can keep my Na value while still removing the row that has the 3 in it. So remember, this is what it looks like originally. There's a 3 and an Na, and everything else is less than 3 for sure, because it's 0, 2, or 1. And here we have our 0, 2, and 1s, but we keep our Na because we asked for them, that it would be less than 3 or is an Na. There's a really nice function if you just want to get rid of NA values for a particular variable called drop NA. And so you can pipe your data into the drop NA function and then say that we want to get rid of NA values for dog. And here we've removed that one NA value. But if we can also use it on an entire data frame to remove any missing data from any column. So if we just use it with open parentheses here, we get all of the NAs removed from both dog and cat. So all of these rows are removed. So even though this row has an NA value only for dog, it gets removed, as well as this row because it's an NA for cat, this row, and this row. So we're only left with these two. Okay, so sometimes we want to drop all of our columns that have any missing data. And the Nanyar package has something useful for this, which is the miss variable which function. And so it helps us to determine which variables have missing data. And so if we have if we add a new variable to our data frame with our dog and cat data, and we call this test, and it's just a vector of integers. So now we have this new variable here that doesn't have any missing data. And we ask which of the variables within data frame are missing. So in other words, which columns have missing data. We see that dog and cat have missing data and test does not show up. So if we want to select for only the columns that are not having any missing data, we can say not miss var which, because that is indicating which variables have missing data here. So we're saying not dog or cat, and so we only get test. So this can be nice if you want to just get rid of columns that have missing data. Because if we were to use our drop NA function, we would remove rows that had NA values for test. So like, for example, this row and this row would be removed. Okay, removing columns with a threshold of % missing. So sometimes we've been requested in other classes for this particular case, and it's a little bit complicated. So I'm going to try to walk through it slowly, but just know, like, if this seems a little confusing, that's all right. Don't worry about it. This is just in case you have this particular situation where you need to remove a % that's missing. So remember that our isNA function basically just gives us a conditional true or false about whether a value is NA. And so if we use it to a data frame, we'll get information like this. Previously, we were just looking at a vector. Now we're looking at a data frame. And so this value must have been NA, which if we go back, we can see that the second row for dog is NA. And the first row was for cat. So if we use the fact that trues are evaluated as ones and false are evaluated as 0, then we can get means across each of these columns by using the column means function on this data that we created here. Because here we're just looking at isNA data frame, and head is just showing us the top part of it. So here we see for the dog column that we had around 16% missing. For the cat column, we had 50%. And for the test column, we had 0. So all of the values were false for this column. 50% of the columns values were false for cat, and just some of them were true or isNA for dog. And so now that we have these values, we can do a conditional and say, what threshold we want to remove by. So let's say that we only want data where it's, we want to select columns for which these values are less than 0.2. And so remember, if it's totally complete, then we have 0 missing. So we want to have less than 20% missing. So now we only have dog and test because this was 16% and this was 0. All right. Now, sometimes we have values in our data that we want to be NA, but aren't yet. So often that's a 0 or it could be some other value. And there's a really great function called NA_if of dplyr that can help with this. So let's say that in our data frame where we have zeros, we would like them to be NA. We can use the mutate function to take our existing dog data and convert the NAs of dog to be 0. So if it is NA of dog, we want to, sorry, if the 0 of dog, if we have a 0 in dog, we want to make it NA. Sorry for that, I said it backwards. And so it's a little easier to see here. Here's our 0. We've converted the 0 to NA. So just like typical, we're first specifying what data we're trying to change. And then this is specifying what the replacement is, that we're replacing zeros for NA. Okay, so it's important to think about what your NAs actually stand for in your particular data. So be careful. So sometimes you want to remove your NA values, sometimes you don't. So it's important to think why you have an NA value, what it means in your survey or whatever it is that you're working with. Is it a case where an NA value is basically a 0 and so it wasn't reported, or could it be something like it's an extreme value, it could be really high, it could be really low. This varies. So if it's something that's more like a 0, that might be something that you actually want to keep in your data. So as an example, you might have a survey about youths smoking, which we had some of that earlier. And we might get a report if it's about the number of times that a youth has smoked recently. We might get an NA if a student has never ever tried cigarettes. And so if we're trying to figure out across a certain group of individuals how many cigarettes were smoked this week, then we might want to convert those to zeros. So you just kind of need to think about what your NA values might mean and what your sample size is that you're really looking at. Do you want to keep those values or not? So just a word of caution about percentages, about whether you should include NA values and percentages or not. So here I'm showing you how to calculate a percent here. I'm using some data called red blue, where I have 3 blue values, 3 red values, and 3 NAs. If I calculate a percent by using the mutate function, I'm creating a new variable called percent, where I'm taking this column called column count, which is the number of times that each of these comes up, and I'm dividing by some denominator. In this case, I'm dividing by our column count values summed together. So 3 plus 3 plus 3, which would be 9. So what I did here is I pulled the column count data out of this red blue tibble, and I summed across all of that to get 9, 3 plus 3 plus 3. So here I get 30%, 30%, 30%, but maybe I don't want to keep my NA values. Maybe my denominator should actually be the dropped NA version of red blue, so that I'm really assessing that 50% were red and 50% were blue. So just keep this in mind when you're calculating percentages to think about what your NA values mean and what denominator you should be using. Okay, so in summary, we have our isNA function and also our others like isInfinite, in case we're looking at that, that help us to check for NA values. Our count function is super helpful for doing this for particular variables, but we can also use nice functions like ggmisvar from NannyR to get a cool plot of where our missing data is. We can use the filter function nicely to filter by conditions, but remember that this will remove any NA values unless we add this or is NA to our condition. If we want to get rid of NA values, we can use the drop NA function, which will remove any rows that have NA values for a particular variable if we add a variable inside, or the entire data frame if we put nothing inside of it. Remember that NA values can change your calculations, so think about what they mean. Okay, and so with that, we will go to our lab about missing data. There we go. And everyone else see it.
Looks good.
So now we're going to talk about recoding variables, which is one of my favorite topics because it's super important. Okay, so let's say we have some data called data diet. And in this data, we're asking samples about their gender and what weight they started at and whether they had a weight change. And so they're on different diets. There's an A diet and a B diet. We get their initial weight and we get the weight change, whether they gained weight or they lost weight. And we can see here that gender is coded in a lot of different ways. So this is like a comical illustration of some of the things that you'll see in really large data sets. So this is a pretty small table. There's only 12 rows, but we have many different ways of describing someone that was considered male, because we have the word male, we have a lowercase m, we have an uppercase m, we have the word man, and all sorts of things. So this is the kind of thing that you would often see if someone hands you data from a survey by someone that maybe wasn't aware of the challenges of dealing with this type of data during the analysis portion. So if we use our nifty count function to see how many times we have each of the different unique values for gender, we see that we have 3 different ways of coding someone that answered the survey as female. We have 4 for someone that answered as basically male, and we have 2 different options for like a non-binary version. And so if we were to try to fix this, because this is going to make it really hard to compare the different groups here, we would want to use a function called recode from dplyr. So we could, try to do this by hand. We could try to use Excel or something, but we're probably going to make mistakes. And so this is a way to do it in a much cleaner way. So let's slowly go through this. We're using our mutate function to update the variable that we want to change. And so we would put the name of the variable we want to fix. In this case, we're fixing gender. And then we would use the recode function, show that there, around the variable that we're trying to fix. Here it is again, gender. And then we would have our old values equals new value. And so here we have male, we want capital M to be male now, lowercase m to be male, etc. So that we have a consistent, only 3 total unique ways of coding gender. And so here, once we run this, we see that we have a nice data set here where we can see who had what diet and how many we had of each. And we no longer have this confusing setup where we have a lot of different coding. Okay, so there's also a really nifty function called case when that's a little bit more flexible. So you'll notice that in recode, we have to have our old one thing at a time. So the old thing and the new thing that we want it to be. But case when allows us to do lots of fancier things. And if you're used to if else statements for other languages, this is basically a fancy version of doing that that's a little more intuitive, and it allows for really nice nested versions of that, which can look really complicated when you're using if else for a really fancy case when. So in this case, we're using the case when function, the variable that we're fixing, some condition, this tilde sign, and the value that we would get if that condition is met. So here again, we're mutating gender because we want to change gender. And we're saying when the case is that gender is exactly equal to male, or capital M, the value should be male. So here we're just changing one thing, not all of them, just one. So let me read through that again. So we're mutating or changing the gender variable so that when gender is exactly equal to capital M, we're changing it to male. And you'll notice here that we have a lot of NA values now. So we have one value for male that got changed. But we see a lot of NA values. This was our capital M that got changed to male. We actually lost our other male. This one was a male value. So that's not great. So how do we fix that? The reason this is happening is that case when automatically assigns everything else to NA unless you specify what should happen for values that don't meet the condition. So it's possible that you fill up everything with every single value is going to meet a condition that you describe, or you can use this true argument, which is basically, this is true for all other situations, what we're going to do with the values that do not meet the other conditions. And so here, looking at this, we're saying, let's change gender so that when gender is exactly equal to M, make it male. And for all other cases of gender where it's not equal to capital M, keep it the way that it was. So use the original values for gender. I see some people are taking notes. I'm going to pause for there. I'll do that again. So I'm changing the gender variable so that when gender is equal to exactly M, I will change it to be male. And for all other cases of gender, so where it does not equal exactly M, I'm going to stick with the previous version of gender. And so now here I recoded my M as male, but I've also kept my other versions of values for the gender variable. Okay, so this can be really useful because we can recode everything here now using case when like this, where we can say for all these different values, including when it's male, because otherwise that would get missed, make it male. For all these types of values, make it female. And for these, make it other. And then we end up with a data set like we want, where we only have 3 unique values for gender. I'll show you soon how we can improve on this, because we might even make a typo here, right? Or we might forget to use male, and then we'll have NA values. And so I'll show you in a minute how we can make this even better. But the great thing about case-when is for really sophisticated comparisons. So for example, let's say that we want to make a new variable called effect. So case-when can also help us make new variables. And this effect variable is basically going to show us whether a person lost weight or stayed the same or gained weight. And that's going to be based on the weight change variable. And so if make this new variable called effect when the weight change variable, this other variable called weight change, when the value is greater than 0, make the effect variable value be increase. When weight change is exactly equal to 0, make the value be same. And when weight change is less than 0, make the value of effect be decrease. And so when we look at our data, it makes it a little more clear. Here we can see that we have a positive value for weight change here. And so we see the word increase. And here we have a negative value, it's less than 0. So we see the word decrease, which might be a little bit easier to look at. And now we also have, a clear indication of who stayed the same. And so this might be helpful for creating a plot where we wanted these words or doing an analysis. Okay, so that's the case-when function. We're going to keep using it in just a bit to show how we can improve on this recoding of our very, very messy data in just a bit. But first, we're going to talk a little bit about strings. Okay, so first I'm just going to share my RStudio screen real quick, because there was a question about the in notation, which we covered a little while ago, so it's been a bit. So basically it's just looking, is there a number 1 within this vector? And it will give us the answer true if there is. But say we said 5, the answer will be false. So that's what we were using there in the code. So stop the share. Show the screen again with the code. So here we're asking, is gender, or is the value within these values? If it is, so if it's equal to any of these, it's the way to do exactly equal, but for many different patterns, because we could do like the really long way for each one. If gender equals exactly male, capital M, if gender equals exactly male, if gender equals exactly man. But this is the way to, instead of doing double equal sign, we can have a shortcut to look for all of these. Hopefully that clarifies that question a little bit more too. Okay, so now we're going to talk about strings. And so R can do much more than find exact matches in our data like we're doing with case-when, with these, for example. It can also look for part of a string, and we're going to use the stringer function for that, or the stringer package, I should say. And so if you're familiar with grep or gsub for other languages, or you have some familiarity with base R, we're kind of going to talk about equivalencies to these, but using the version from stringer. So stringer functions start with the letters str and an underscore. And there's a variety of functions that are very helpful for many different cases. So for example, we're going to talk about a few. We're going to talk about str detect and str replace. So they search for matches to a pattern and do something with that. So if there is a pattern that is found, str detect will return the value of true, and str replace will look for a pattern and replace that with a provided replacement. So I'll go through those in detail. So let's say that we have a vector that has several strings in it. It has cat, dog, and mouse. And I want to use str detect to work on this vector. And note that these functions mostly work on vectors. So you would need to pull that data if you were using a data frame to pull it into a vector. So okay, we have a string argument, which specifies where we want to look for a pattern. And we have a pattern argument that specifies what pattern to look for. So here we're going to ask in the x string, so string equals x in this vector, look for the pattern of lowercase d. And again, we're going to get a logical output of true or false. And so for cat, we do not see the letter D, so we get a false. For dog, we do, so we get a letter true, or we get the value true. And for mouse, we do not see it, so we get a false. str replace instead is going to not only detect where that value is, but also replace it with something. So the difference here, with the same arguments, except we have an additional argument called replacement, which is where we specify what we want to replace the pattern with. And so in this case, we want to replace lowercase d with capital D. And so here we can see that now we have replaced lowercase dog with capital dog. There's also a really helpful function called str sub that does part of a string. So Ava put something in the chat for someone who asked a question for something that starts with something. This is kind of a variation of that that's helpful. So say you wanted to look at the inner part of a string, you could do that with this function. So it lets you subset part of a string, and it has a few arguments. It again has a string argument just like before, which is the string that you want to check and or work with. And there's a start argument, which specifies where to start. And this is a typo, this should be in an end argument. And so here we are going to start at position 1, and we will end at position 2, and we want to subset our existing strings of the vector x. And so here we have taken the first 2 values of each of our strings. So we get rid of USE, for example. And stringer can be really helpful with filter if we're looking for particular values. So we can combine these together. So here we have our diet data, or data diet. And again, this is data that I created earlier. So if you try to run this, you're not going to find that data unless you create it as well. It's not part of R intrinsically. But what I'm doing here is I'm nesting str detect within the filter function. And again, here I have my two arguments that I typically have, which is the string that I want to look at. And in this case, I want to look at the variable gender. And the pattern is capital M, and it will pull out anywhere where it sees an M. So it can be that it starts with an M, and it could also be that it ends with an M, or it's just somewhere in the string, which is kind of nice. Oops, sorry. So now we're going to return back to case when, and we're going to improve on what we did before, because now we know more about stringer, and so we can do some additional things with stringer now. So just a reminder, when we looked at the gender variable of our data diet, we had all of these different ways in which gender was coded, which is super frustrating to work with if we're trying to plot the data or perform analyses. And so we had this way in which we changed it using case when, in which we changed the gender variable using mutate, and the case when gender happened to be equal to any of these values, we changed it to male, etc., etc. But we could make a typo or forget to do one of these, and that could result in an error. So this could be improved. So we can use this little caret symbol to indicate the beginning of a string. If you wanted to, you could use the $sign to indicate the end. And we can make this really clean and nifty. So we can take our case when function and nest within that str detect. And we're working with our gender variable, so that's our string. And we're going to look for patterns that start with M or lowercase m or capital M. So remember, this is our OR syntax. So we can look for multiple patterns. And if we have either of these patterns, we want to recode it to be male. Similarly, if it starts with a lowercase f or a capital F, we'll recode it to female, and lowercase o or capital O. I could have put all of these. Yeah, no, that's basically, I think, as small as I could make it here, to recode everything in a way that I think is programmatically really nice. And so we end up with, our 3 unique values for gender. And, we might feel like this, like, oh, we didn't have to recode this with a ton of code. And it's really clean and super reproducible. So that can be really nice. Case when is super powerful. All right, and so we're going to cover one last thing. I saw people, did you need any more time with this? Remember, the slides are available on the website too. So we're going to cover one last thing here, which is working with data where we might want to separate or unite across columns. And so let's say our data looked like this instead, where we had the diet that people were on and an underscore and the effect, whether it was increased, their weight was increased or decreased. So this isn't great. This is what's called messy data. It's not in tidy format. Tidy format would mean that each individual thing, each individual value for a column is a single value. Here we have sort of 2 values stuck together, and that's a problem because say we want to assess just those that increased versus decreased and figure out which diet it was. Right now we can't do that, so that's annoying. So how can we fix this? So the tidyr package has a really, really helpful function called separate, which can help us to clean this type of data and split a column or separate it into multiple columns. And so here we have a few arguments. We have a col or column argument that specifies which column we want to separate. We have an into argument, which specifies the names of the new columns that we're creating from the col column. And we have a separate argument, which specifies what we want to separate by. So going through this example, recall that our data looks like this. We have a variable called change, and we have values and then an underscore and a word. So we probably want to separate by this underscore. So we'll say that we want to change the column called change, and we want to split it into new columns, and we're going to name the new columns diet and change, and we're going to separate that based on where the underscore is. And so now we end up with two columns where we only had one. We have a diet column and a change column. So this is much better to work with. So just to show you again, this is what the data previously looked like. We had a column called lowercase change, A, B underscore increase or decrease. And we split that now into, so this was our lowercase change column. We split this into, we made a new uppercase change and uppercase diet column that we see here now. But sometimes we actually want to unite columns and not separate them, but put them together. So we have another function that's helpful for that called unite. And it's similarly set up with the same type of arguments. We have a call or column argument that specifies the new name, just like, here we're looking at the argument we want to split. Here we're specifying the argument, the name of the new column. So it's a little bit different. And then we have our separate argument, which is what we have been separating by, but we want to use for our combination. So that's kind of the same. So this will be easier to understand when we go through this example. Say we have data like this, and we have these subgroups that we kind of want to put together. So we have maybe an individual ID and the visit time when they came. And we'd like to put these together. To do that, we can use our unite function. We're piping our data frame into unite. We're specifying the name of the new column that will be the name of these columns combined. So we're going to call this unique ID. And we're specifying which columns we want to combine. We want to combine ID and visit. And this, we would like to use the underscore as the separator between the two. And so in the new unique ID column, we now have an underscore between these values from the previous two columns. Okay, so in summary for recoding, we have our recode function, which is similar to case when, but it does simple recoding. We can only do, this, we have a value that we would like it to equal this new value. We can't do a really cool condition, but just a simple swap. Whereas case when allows us to do conditions. And typically we would work with entire values, but there are some nifty workarounds like Ava put in the chat. Otherwise, we can combine it with stringer to do part of values. Recall that case when needs to have an assignment for the values that do not meet the conditions unless you specify all of them. Otherwise, they will all end up being NA. So if you want to keep the original values, you just assign these to the name of that original variable if you're changing a variable. And then stringer is helpful for looking at parts of values. And for example, we can use filter and str detect together to look for rows that have a piece of a value within it. So if we're looking for any row that has the letter A within the value, we can do that. But there's also lots of other string manipulation functions that we can use that are super helpful. We only covered str detect, replace, and set, but there's many, many more. So if you work with strings a lot, I recommend checking it out. And then we talked about separate to split columns into additional columns and unite to combined columns. Okay, so with that, we will go on to the lab.